This is PowerPoint Chapter 6a, Precipitation Extremes. Now, remember back in Chapter 4 we talked about clouds and the different kinds of clouds and condensation. Chapter 5 we talked about conditions of stability or instability. Instability, of course, being that condition that's conducive to the formation of clouds. And Chapter 6 will discuss precipitation that comes out of those clouds. So this chapter will focus on the following: the processes through which precipitation forms in clouds and falls to the ground, the different kinds of precipitation, which is a little bit more complex than just saying, okay, it's rain or snow, and then extreme precipitation events around the world, either an excess of it or a lack of it. So what is precipitation? Basically, that's any form of water that falls from a cloud that reaches the ground. It could be frozen or it could be liquid. Now, a cloudy day doesn't necessarily make a rainy day or a snowy day. Now, I'll give you an example. Right out of your textbook. If you're familiar with the California coast, you know there's a lot of fog, low clouds in the summertime. Eureka, California in August, if you can just sort of think about that for a minute, way up by Humboldt State. The daytime sky in Eureka, California in August is overcast more than 50% of the time, but the average precipitation for August is only 1/10 of an inch. So just because it's cloudy doesn't necessarily mean that it's going to rain or snow. We are now going to in-depth examine the processes through which precipitation forms in clouds and ultimately reaches the ground. The first process has to do with talking about condensation nuclei and cloud droplets and raindrops. You might recall that in a previous chapter we defined condensation nuclei as being those tiny, solid, microscopic sized particles in the atmosphere, such as air pollution, volcanic ash, blowing dust, sea salt, whatever, microorganisms, on which water vapor molecules cling to in order for condensation to occur in the atmosphere, i.e. cloud formation. So condensation nuclei attract water molecules in order for cloud droplets to form. Once cloud droplets form, then of course you've got to get enough of those cloud droplets in a volume of air for that volume of air to then rise, expand, cool off, and to have a cloud form. By volume, it takes 1 million typical cloud droplets to make one typical raindrop. So that's pretty astounding when you think about it. If you look at that graphic right there, a typical cloud droplet is 0.02 of a millimeter in diameter. A typical raindrop is 2 millimeters in diameter. So per unit volume, we're not talking about diameter now, volume, it takes 1 million of those cloud droplets to make one raindrop. So I want you to think about that miracle the next time it rains on top of your head. And if you're lacking an umbrella and you're walking out in the rain, we'll just sort of celebrate the fact that you can walk up to your friend and say, hey, let me dazzle you with science, and say, did you know that it takes 1 million tiny cloud droplets to make one lousy stinking raindrop? That really puts things in perspective. All right, enough of this seriousness. There are two processes through which scientists have found that precipitation forms in clouds. One of them has to do with warm clouds, and one of them has to do with cold clouds. So we're going to discuss the warm clouds first. Where do you find warm clouds? In the tropics, near the equator, where the clouds go high enough into the atmosphere where, because of the thickness of the troposphere, it's still relatively warm up there, and you don't have ice crystals in the cloud. Precipitation forms in warm clouds through something called the collision coalescence process. The temperature in the cloud top is warmer than 5 degrees Fahrenheit, or minus 15 Celsius, in the tropics. You have a mix of large and small water droplets in the cloud. The large water droplets fall faster than the small water droplets, and so they overtake and collide with the small ones. This is the coalescence part of that process. This is especially enhanced if the water droplets have opposing electrical charges. The process is also enhanced the longer the cloud droplet spends in the cloud, bounced around by updrafts and downdrafts and so on. And if enough cloud droplets coalesce or cling together, a raindrop forms and then falls from the cloud, reaches the ground. raindrops usually don't exceed 5 millimeters in diameter. When they get that big, they tend to break apart and form baby raindrops, if you will. And the whole process starts again. So figure 6.3 in your book shows the collision coalescence process in the precipitation formation of warm clouds. That's in the tropics. Now, where you live in Fresno, we don't live in the tropics. We live in the mid-latitudes, so we have cold clouds. The name of the process through which precipitation forms in cold clouds is called the ice crystal or Bergeron process. Bergeron was a scientist that helped to quantify this back in the beginning of the 20th century. Precipitation formation in cold clouds is called the ice crystal or Bergeron process, taking place in the middle latitudes and high latitudes. You live in the middle latitudes. What's the latitude of Fresno? It's 37 degrees north latitude. The top of these clouds, where we live, go well above the freezing level in the troposphere. That's the lower layer of the atmosphere learned about in Chapter 1. The coexistence of supercooled water droplets and ice crystals cause precipitation to form in cold clouds. What is a supercooled water droplet? That means that water droplets that don't turn into ice crystals at temperatures at or below 0 Celsius. It's one of the miracles of pure water, where water can exist as liquid in a cloud at temperatures well below 0 Celsius. The ice crystals, however, do of course become more numerous the higher the cloud is up in the atmosphere at higher altitudes. The water droplets may not always freeze at temperatures below 0 Celsius because of the unique properties of pure water. The smaller the amount of pure water droplets in the cloud, the lower the temperature at which they freeze. Ice crystals form in cold clouds if there are solid ice-forming particles present in the cloud, which are called ice nuclei, which, by the way, are rare in nature. They're not very abundant. Just like the condensation nuclei in a warm cloud, same sort of thing. But this sort of mimics the structure of an ice crystal. Now, in the cold cloud, the vapor pressure surrounding the ice crystal is lower than the vapor pressure surrounding the water droplet. As a result of that, water molecules are attracted to the ice crystal at the expense of the shrinking water droplets. This is called accretion, which then is a constant supply, a source for moisture for the ice crystal, which then grows and gets big enough and it falls out of the cloud as either a snow pellet or a snowflake. Now, you may have heard the term cloud seeding before. This is an artificial way of adding ice nuclei, which remember are rare in nature, they're not abundant in nature, to clouds with the right temperature and vertical profile to possibly coax a few more of those supercooled water droplets to cling to those extra artificial ice crystals and become additional snow. At a General Electric laboratory in the late 1940s, there were experiments that were conducted by scientists Schaefer and Langmuir with dry ice, which is a substance that mimics an ice crystal that can attract supercooled water droplets in a cloud, cling to the pieces of dry ice, the molecules of dry ice, and then become snowflakes and fall to the ground. Later on, a scientist by the name of Vonnegut did the same thing with silver iodide, which mimics the crystalline structure of ice. You may see that name of Vonnegut as familiar to you. Well, this Vonnegut is the brother of the author Kurt Vonnegut. His brother was a physicist for General Electric and was a scientist. Silver iodide has a crystalline structure that's hexagonal, much like a natural freezing nucleus in the atmosphere. It's very effective at temperatures at about 25 degrees Fahrenheit, meaning -4 Celsius, and lower. With dry ice or frozen carbon dioxide, that has to occur at much lower temperatures in order for it to be effective to cause supercooled water droplets to be attracted by a piece of dry ice. But it's effective at warmer temperatures with silver iodide than it is with dry ice. One of the ways in which silver iodide is added to clouds is by aircraft. They burn flares on the aircraft. They fly into these clouds, not just any cloud, but it has to have the right temperature and vertical profile in order for this to occur. Now, the effectiveness of cloud seeding to increase the snowpack in the mountains is debatable. The proponents of it do claim that increases in snowfall in certain watersheds that are seeded this way can be on the order of, say, 5 to 20% increase. But it's not without the realm of possibility for this to be quite cost effective for water districts, especially here in California, which get their water from snowmelt. So if you can add 10% to the snowpack that would not have occurred otherwise by simply adding fake ice crystals, if you will, to a cloud so super cool water droplets can adhere to them and make additional snowflakes, then that may be cost effective. It might be worth it for a water district to, say, spend $250,000 a year to have a company come in and do cloud seeding. Inadvertent cloud seeding can occur as a result of heavily polluting industries where precipitation might increase downwind of those areas. Now let's talk about the types of precipitation. Well, rain is kind of a no-duh, but basically, I will tell you, there is a scientific definition of rain. It's liquid precipitation that falls from a cloud that upon reaching the surface, the drop is equal to or greater than 0.5 millimeter in diameter. Raindrops, as I mentioned before, rarely exceed 5 to 6 millimeters in size. Drizzle are fine uniform drops that are liquid that fall from a cloud, which are less than 0.5 millimeter in diameter. And virga, as seen here in this picture, is precipitation that evaporates before it reaches the ground. Maybe you've seen that from time to time. Let's talk about snow. Seems pretty straightforward. That's frozen precipitation. Snow can fall about 300 meters, about 1,000 feet or so, below the freezing level in the atmosphere before completely melting, or even lower if the air that the snow is falling into is quite dry, which tends to slow the melting process down. Snow can fall as occasional flurries or snow showers or more intense snow squalls, and snow comes in various shapes and sizes and appearances due to many factors, including snow grains and snow pellets. If there's a lot of snow on the ground and it's being blown around by very strong winds, we call that a blizzard. If you have too much snow on a steep mountainside and it starts to rapidly cascade downhill, we call that an avalanche. This chart, figure 6.15 in your book, shows the average annual snowfall in the United States. And obviously in the southwestern United States, away from mountainous areas like the Southwest Desert and the San Joaquin Valley, you don't get much snowfall. And of course on the Gulf Coast of the U.S. you don't get much snowfall. That's pretty self-explanatory. Most of the snowfall is in the Intermountain West and around the Great Lakes. This table, table 6.1, shows the snowiest cities in the United States with over 10,000 population. Truckee, California is in there. They've got 18,000 population. But the snowiest place in the United States by far is Marquette, Michigan, which is on the Upper Peninsula right near the Great Lakes there. They get a lot of snow. And you can look at that chart in more detail if you'd like. Sleet is a unique situation where the precipitation originates as snow from a cold cloud, gets to a layer of the atmosphere where the temperature warms up, and it melts and becomes rain, and then that rain falls into a deep layer of freezing air right near the surface and then results in little ice pellets that form. We don't get sleet around in California very often. It's more common, say, on the East Coast. Now you can get what's called rime or black ice. Rime ice is super cool fog droplets that accumulate on surfaces that are really cold, like that tree in the top right-hand picture. Black ice can be a problem for motorists, of course, when you have precipitation that freezes on roadways and bridges and so on. Rime ice can also be a major problem as well as clear ice for aircraft, especially in very cold climates, because if you get ice accumulating on an aircraft wing, that tends to change the shape of the wing, makes it difficult then to control the aircraft. So they constantly have to de-ice aircraft in flight and on the tarmac. This is really a major mess. This is called an ice storm, which is an accumulation of freezing rain. When you have precipitation starting out as snow, melting and becoming rain, and then falling into a very shallow layer of very cold air near the surface, and all the surfaces are also very cold, and so the rain freezes on contact and makes a mess of everything. You can have power outages for days and weeks, hundreds of thousands of people affected by what is called an ice storm. These are the various vertical temperature profiles of different kinds of precipitation: snow, sleet, freezing rain, and rain. You can study those in greater detail as you read the chapter. Then there's hail, pieces of ice from the sky which can be round in shape or irregular in shape, transparent or partially opaque. They can be the size of small peas all the way up to golf balls and larger. They can really hurt you if you hit your head. The article in the hyperlink, please take the time to read it, is about how a larger hailstone fell recently, which surpasses the record that's published in your book with respect to the size of hail. Basically, frozen raindrops or even insects act as embryos, and it takes about 10 billion cloud droplets to form one hailstone. They accumulate layers of ice as they go up and down in the updrafts and downdrafts, and finally fall to the earth. This shows you the average number of days annually with hail in the United States. Pretty self-explanatory. Here is a video that you can watch on your own.